Welcome to my presentation on the PA-44 Seminole. I'll be presenting on the propeller, landing gear system, and fuel system. So we'll start off with the propeller. We have a two-blade constant speed controllable pitch feathering propeller. It's manufactured by Hartzell. And on the left side here we have the specifics of it, the propeller diameter, minimum and maximum. And then we have the more important stuff, that it's a constant speed, hydraulically actuated, and full feathering propeller. On the right side over here, we have the engines. So we have two Lycoming IO360 engines. The IO360 is exactly what we have in the Archer. This is just a different engine model number. They're still rated to 180 horsepower, 2,700 RPMs. They're still fuel injected, four-cylinder, direct drive, horizontally opposed, and air-cooled engines. Next. Propeller pitch is controlled by two things. It's controlled by oil pressure from the governor on the left side of the prop hub in this picture. And then it's controlled from the right side by a large spring and some nitrogen pressure. So the propeller governor supplies engine oil at various pressures through the propeller shaft to maintain the constant RPM settings, and the governor controls the engine speed by varying the pitch of the propeller to match the RPM that we set with the propeller knob. So if we push this prop lever forward, it's going to push down on that speeder spring, and it's going to bring those flyweights in. When those flyweights fall in, the pilot valve will drop down, allowing oil to enter the prop hub from the governor. Once that levers forward and that oil enters the prop hub, it's going to push the prop to that higher angle, which is for takeoff, and it's pushing against that spring and that nitrogen that's stored up in the prop hub. If we pull the lever back, the opposite happens. The flyweights are going to fall outwards because that spring is going to come upwards. When they fall outwards, they're going to bring the pilot valve up, and it's going to open up that area for oil to flow out of the propeller hub. So we can see here, oil is flowing out of the propeller hub, and it's allowing that propeller to go to a lower RPM setting, a lower pitch setting, or a higher pitch setting, lower RPM. And all that oil is flowing back out to the oil sump. And yep, that's the same picture. All right. And then, so we have our propeller control levers. They're in the throttle quadrant. The middle ones, they're blue. They can be pulled back to a low RPM setting, and they can be pulled all the way back to the feather setting. So the feather setting, again, is going to be when that blade is edge on into the wind and creating as minimal drag as possible. Next, we have unfeathering accumulators. So those store engine oil under pressure from the governors, and they are used to release that pressure when the prop is feathered to unfeather it. So it's going to shoot all that pressure into the prop hub to unfeather the propeller. The reason we need this is because when we're at a high airspeed and those blades are stopped edge on into the wind, it's going to be really hard for us to get them rotating because we have no surface to push on yet. So those accumulators help to kickstart that system. Another system that we have is a feathering lock. So when the propeller is spinning fast, this feathering lock is disengaged via centrifugal force, so it's not able to engage. But then once the propeller gets below 950 RPM, that feathering lock will fall into place because of a lack of centrifugal force, allowing that prop not to be feathered. So it'll block the prop from being feathered if we're below 950 RPM. And this just helps us so that we don't accidentally feather the prop while we're on the ground. So this is a diagram of the accumulator. So you can see on the bottom left there, it's got the stored nitrogen, and that's aiding the high pressure oil in boosting back into the pump or back into the hub to unfeather the prop. And yep, there it goes. You're going to push the prop lever forward, flyweights are going to swing in, pressure accumulator is going to pump all that pressure into the prop hub. Move into some abnormal scenarios we might run into. So we got the propeller overspeed as well as autopilot overspeed and autopilot underspeed. So those are the recovery procedures for those on the right hand side for the autopilot versions. I'll just quickly explain. So for the propeller overspeed, it's usually caused by a malfunction in the propeller governor, which allows the blades to rotate to full low pitch, which is flat, which is bad. So if we were trying to descend and we have flat blades, that propeller is just going to be spinning way faster than necessary, and it could cause engine damage. Next slide. We have our MFD engine indications page. So you can see up in the top left, we have manifold pressure and RPM. So we're going to be using our throttle and prop lever to set those. And then the rest of our engine instruments here as well, they don't have as much to do with the propeller system. On to the landing gear system now. So we have a hydraulically operated, fully retractable landing gear system, tricycle gear. The retract speed is 109 knots and the extend speed is 140 knots. It's an electrically powered reversible hydraulic pump, just like in the Arrow. And just like in the Arrow, the gear selector switch has an up and down position with a detent, so you're not going to need to pull that handle out before you can move it up or down. And gear retraction or extension normally takes about 6 to 10 seconds. So landing gear, when it's being retracted and extending, has limit switches for up and down. Electrical limit switches stop the flow of current to the motor of the hydraulic pump when the gear get up or when they get down. So it'll turn off the pump electrically. Springs assist in gear extension and in locking the gear in the down position. So springs along with gravity. And then they'll lock into these down hooks, and the down hooks will engage, and springs will maintain the force on each hook to keep it locked until it's released by the hydraulic system. There's also a mirror on the left engine that can help us see the position of our nose gear. And then in the bottom right here, you can see where the gear lever is on the instrument panel, and you'd see the up and down position. This is a schematic of the landing gear hydraulic system. So as you see, we have a high pressure side and a low pressure side. High pressure I put in green, low pressure I put in red. Um, the high pressure side is going to be used when we're trying to bring the gear up. So you can see it's going to be pumped into the bottom of all those cylinders and it's going to raise the gear, uh, pushing that low pressure oil out of there. Vice versa, when we want to put the gear down, oil is pumped in through the low pressure system to push those pistons back out. And they have a series in the system. We have a series of relief valves and um, restrictor valves that just help control the pressure to make sure we don't exceed any pressure limitations in the system. To check the status of our landing gear, we have 4 different kind of indications that we can get. We'll have a 3 green indication when the landing gear is down and locked. We'll have no lights when the landing gear is up. If the landing gear has failed in some way, we'll have red lights. And then if the landing gear is in transit, we'll have the gray squares. The gear can be in an unsafe position. So there's 3 unsafe positions in which we'll get a check gear warning message, and that'll just be kind of repeating. It'll say check gear, check gear, check gear, and that'll sound when the gear is not down and locked in these 3 situations. If the manifold pressure is below 14 inches on either one or both engines, if the gear selector's in the up position while we're on the ground, and if the gear is not down and locked and the flaps are extended either to the second or third notch. So that caution message will be a caution message as long as we're above 400 feet AGL. But as soon as we descend below 400 feet AGL and one of those conditions is not met, it'll become a warning message to try to get us to extend those gear down. We also have a squat switch, same thing as we had on the Arrow. It's on the left main gear, and when there's weight on the squat switch, it prevents us from raising the gear. When there's not weight on the squat switch, it allows the gear to be raised, just so we don't inadvertently raise the gear while we're on the ground. Next is the emergency extension lever. So it's on the left side of the gear lever, and it's got a cover on it and a bar across it, so you don't accidentally pull it. What it does is when you pull that emergency gear extension lever, it's going to release all the hydraulic pressure from the system, and it's going to allow gravity to extend the gear, basically putting them into a free fall. So what's holding them up is hydraulic pressure. When that pressure is released, the gear are free to fall down into their down and lock positions. We also have a hydraulic reservoir, just kind of like we do for the brakes. Um, we have a steerable nose wheel that's assisted by little bungee cords, steerable through 30 degrees, and also has a shimmy dampener to dampen any shimmying that might be going on. We have 3 tires, and we have air oil struts, also known as oleo struts. Now we'll go into the fuel system. So we've got two 55-gallon fuel tanks. So that would be 110 gallons total. 108 gallons of that is usable fuel. And the minimum fuel grade we're allowed to use is 100 octane. We usually use 100 low lead, which is blue. This is our fuel schematic for the Piper Seminole. It has two sides because we have two engines. The fuel tanks are located in the engine nacelles. Again, those hold 55 gallons each, with 54 being usable gallons of fuel. They both have a drain and a vent on them. And from those tanks, the fuel will flow through the fuel selector valves, where we have the three positions that we'll talk about later. And from the fuel selector valves, they'll flow through the fuel filter and sump. Those are the things that we can sump on the side of the plane to check the filter status. After the filters, the fuel will flow through the electrical fuel pumps and then up to the engine-driven fuel pumps, then to the fuel injector servo regulators, and then into the fuel flow transducers, which will send fuel flow data to our uh, displays on our MFD. And then from those fuel flow transducers, they'll flow to the fuel flow divider, also known as the spider valve. From the spider valve, it's going to go into each fuel nozzle and into each cylinder. There is one bypass on the left engine, right after right before the sump. It's going to flow to the heater to power our heater if we have that on. All right, next we have the fuel controls quadrant. So it's located in between the seats, kind of just rear of the rudder trim. So we have two fuel selectors, one for each tank. They have three positions. There's on, off, and X feed. So on, obviously, you're pulling fuel from that engine. So if left engine is on and right engine is on, you're pulling from the left and right engine. If you have them in the off position, you're no longer pulling from that engine. So if the left engine is in the off position, you're not pulling in fuel from the left fuel tank. If it's in the cross feed position, you'll be pulling fuel from the opposite fuel tank. Next, we have fuel drains. So the drains are located on the right side of the fuselage, just forward of the step to get on the plane and just aft of the flaps. And it can be drained from there if you need to reduce weight, or if you are testing the fuel. Fuel pumps. So we have an engine-driven fuel pump and then an auxiliary electric fuel pump to serve as a backup just in case of an engine-driven fuel pump failure. Fuel gauges. We've got the MFD. That'll show us our fuel quantities in each tank, but we need to visually check as well with the dipstick that is provided. So you'll just dip that into the tank, cover the top of it, pull it back out, and you'll read the number to get your actual fuel volume. It's best done when it's on level ground so that you don't have any erroneous readings. And then fuel drains. Before each flight, you're going to check the fuel drains to make sure there's no moisture or sediment in the system. So by draining the fuel drains, you'll